In this video, we are going to look at a fairly straightforward linked list problem where we're adding two integers represented as linked lists, and we output another linked list representing an integer, the sum result. So we have 342 plus 465 equals 807. And that is represented by this linked list, 807. And you notice these are in reverse order. Why is it like this? Often when we have a problem, this problem just makes it more difficult. We represent a grade school algorithm, we represent these structures, we have to manipulate linked lists, but we have to do grade school addition. And how does grade school addition go? We say 2 plus 5, 7, 4 plus 6, 0 with a carry. 1 plus 3 plus 4, because 1 is a carry, is 8. 807. And do you see how we went from this way to this way? When we have a linked list, we want to have the head. I want to have the head. The head of where the addition starts is all the way at the end of the numbers. It's a bit tricky. This is why it's reversed. We do 2, 5, we do 4, 6, we do 3, 4. We're shown exactly how this corresponds to the grade school algorithm. That means we're going to take two nodes, 2 and 5, add them together. Then we create a new node, 7. Then we're going to create the 4 and 6, add them together. But that ends up being 10. Because it ends up being 10, this can be 0, and we need to carry a 1. And then we get the final node of 8. How are we going to go about this? Often, again, as always, we want to lean on our picture, and we want to step through exactly how this is going to happen. And I know a question you may have is, how would we do this if the integers were represented literally as 342 and 465? We know that we're going to have to do at least m plus n time because we have to visit every node. In order to do the grade school addition, every node has to be visited. So we're lower bounded to big O of m plus n. And because of that, we can reverse each of these linked lists with linear time with respect to each of them. That's another big O of m plus n cumulatively. It would be big O of m, big O of n. Reverse this list and then reverse that list. And then we would have this new reversed list. It's just simply reversing them if we get it in this order. And then we would do what we're about to do. Now let's actually walk through how we would do this. We're going to do the same addition here, except we're going to do it on these linked lists. We've already established going right to left. So let's begin adding and start noticing exactly what state we need to keep. Remember, we're going to need to keep track of a carry of some sorts. That'll come down the road. Let's just keep note of that. Let's not write anything down. So 2 plus 5 is going to be 7. Do we need to have a carry? We don't. That means we're just going to create a node, which is 7. But what are we going to be building off of? Remember, going back to our fundamentals. It's often nice to have a dummy head or a head that has no valid value, but it just acts as a start to start building our linked lists, start building a list for addition. So that right there is our dummy head node. We hold reference to that. And we should be literal with the pointers. We're still drafting our example from the picture. Let's put working pointers on both of these lists and put a working pointer on this dummy head. And let's restart. So we have pointer on both lists. We say working pointer of the first list, working pointer of the second list. Do you exist? Okay, what's your value? 2. Do you exist? What's your value? 5. And then 2 plus 5 is 7. And then we're going to append a 7 node onto the next of the working pointer here on this list. And now we need to advance pointers, advance those two guys, and advance the building pointer. And now we're going to say 4 plus 6 is 10. But what do we place here? We're going to want to place 0. But why did we say 0? Well, we do the division of the result by 10. Remember, division by 10 is going to turn this carry value, let's do this explicitly, 10 divided by 10 equals 1.0. And because it equals 1.0, remember when we turn something into an integer, we truncate the ones place. And that's exactly what we want to do with a carry. We want to truncate the ones place, and we want to move this 1 over to the next place. So the carry is 1, and the value we place is 0. And again, advance our pointers, and remember our carry right now is 1. This is probably state we can just keep outside of the while loop. We're going to look at the code. So 3 plus 4 is 7, plus the carry of 1 becomes 8. We append 8 to the list. And what happens ultimately is we move our pointers forward, and there's no more nodes to process. If one of the numbers was longer than the other, we might have one more node to process in one list, but not in the other. This makes us think about our if guard. With our if guard, we want to continue while there's still a node to process. So if this list or this list, so it'd be an or statement in the guard. I think we're ready to craft the code. Okay, we created our function. Now remember, whenever we have linked list problems, it's immediately about pointers. We need to establish working pointers. Establish a working pointer into the head of list 1, the head of list 2, and then we're going to establish a dummy head for the new list we're going to build. And we need a working pointer for that. So let's do the first 2 pointers into these 2 lists. Those are the pointers into the actual lists. These are the working references. And now we need to create the new list that we're going to ultimately return. And let's create that dummy head and also get a working pointer on it. All right, we established pointers, working pointers into the original lists, and we established a working pointer into the new list we're building. And this problem may be straightforward, but these are the core patterns you're going to see in linked list problems. You need workers for traversals, and then you figure out the traversal as you go and address your cases. And now we also need a carry. Remember, if I overflow with addition, 8 plus 8 is 16. I can't represent 16 in a single place under base 10. That means I need a carry. I'm going to need to carry the 1 into the next place, like this. If we had 8 plus 8, we would put a 6 there, and then our carry would become 1, and then it just becomes 16. So that's what we're simulating. Now imagine these numbers are different sizes. We're going to start at the 0 and 2, and then we're going to continue, but this list becomes null. If this list is null, we're still going to want to do additions because the first list has not nullified. That means that we're going to want to continue while either list has a node. And if you're unsure of the while guard, you can just put while true and say in the interview, I'm going to determine this later. So you don't get stuck on it too much because you always can go back and refactor. We're going to want to continue with an or statement. Either this or that has to exist, otherwise break out. Okay, we put our while statement, while the pointer, this pointer 1 does not equal null, or pointer 2 does not equal null. Now we need to extract the actual values. And remember, we might be in an empty state. If the first list has a value and then the second list has no value after we process this first part, if we're here, we don't know which one of these will be alive. So we need to extract the values, taking into account possible null checks. So let's extract the values, taking this into account. Okay, so this is just a shorthand saying if pointer 1 is not null, if that's true, extract its value. Otherwise, just do return 0. If we put 0 here, we can't have the null pointer. If it's null, it's certainly not going to enter that statement. This is just a syntactic sugar for an if statement. When it compiles down, the ternaries just turn into if statements. So this pointer 2, if it's not null, we're going to extract the value. Otherwise, it's just a 0. And when we add, it'll have no effect. So now we have the 2 values. We can take the sum, and then we can compute the carry from this addition. So remember, what is the sum? The sum is the carry amount, which when we first start will just be 0, plus the first number plus the second number. That's the sum. And then, what is the carry? Imagine I have 16. The carry is going to be 1. Remember how we extract numbers using mod and division. If we divide this by 10, we get 1.6. And we're going to truncate the decimal part because integers will truncate all decimal data because we can't represent that in an int. And that just becomes 1. So our carry would just become 1 for the next iteration. The next iteration carry will be 1. And remember, division gets us everything to the left of the decimal. Mod gets us everything to the right of the decimal. If we did the mod here, what is the remainder of the division of 16 and 10? It's just 6. And that's how you'd get what's to the right of the decimal. Now what we're going to do is we're going to actually need that mod. We need to get what's to the right of the decimal. So let's bring that back up. 1 is the carry, but the actual value I want to have at this node is 6. The reason being is if we were to create the node, 6 goes in this position, and then 1 is the carry. We extract this out using the mod, as we just saw. Division extracts the carry. Mod extracts the number to the right of the decimal. That's just the small thing you need to understand about extracting small individual digits or parts of numbers. So now we create the actual node. Okay, now we appended this new node to the end of the list with the sum mod 10. We grabbed off what we do need to represent. The carry is going to take care of itself in the next iteration. And now we can advance all of our pointers. We have 3 working pointers to advance. It's kind of sloppy how we one-line the if statements here, but I'm kind of running out of room. So we have if the pointer 1 does not equal null, advance it forward, and if pointer 2 does not equal null, advance it forward. Because remember, our guard does not guarantee us that either of these will resolve. One of them will not be null, but the other might be null. So we just have to make sure we don't do a null reference and try to call next on a null. And then we advance the building pointer. After we advance the building pointer, we come to the next iteration, and then we keep continuing to append items. And that's going to build this list out. But there's an edge case. What happens if, imagine we saw the 8 plus 8 case. We'd put the 6 in the first place, but then we'd move over and both lists would be gone, but then we'd still have a carry. Well, if we just have the carry, we'll just place it. And this is the final small edge case to this problem. You just need to place the carry. If this while loop breaks out, we need to create a new node for the carry. And I ran out of room, so I'll just erase everything and do that small last line. And then finally, if the carry is greater than 0, we just need to materialize it into a final node. Where the build pointer is, new list pointer, the building pointer, the next becomes this new node with the value of the carry. And then we just return the next of the dummy head, because the dummy head has nothing in itself. It's pointing to the head of the list we were building, so we say dummy head.next. And then that ultimately is going to return the final list added together. So what is the time and space? In terms of space, we are going to use constant space if we don't count the output. If we count the output, then we're going to use the max of the longer list. We're going to use max mn space. That's going to be the time complexity if we include the output. We're going to have a number the length of the longer number. If we had like 1,000 plus 1, our output would be 1,001. And then that would be the length of the larger number. But what if we had 9,999 plus 1? This would actually be 10,000. That would be longer than m. But this is asymptotic. So that'd just be multiplying this by some constant. And if this were to scale, what's going to really happen is the length of the top number is going to dominate in terms of showing the linear behavior. So big O max m, and if we include the output. If we don't include the output, then the space complexity is just constant, because we're not going to be creating auxiliary space. Besides, we had created a carry, we created some working pointers, we're rewiring, but other than that, we're not storing any auxiliary data structures that will scale with the size of the lists. And then for time complexity, we're going to touch every node and do constant work. So that's going to be big O of m plus n for the time complexity. And remember how we were talking about the time complexity when we started, about reversing the lists, how that wouldn't really change the asymptotic result. We still came to linear, multilinear time, big O m plus n. That's just something that can guide your decision-making process if you can project the n time complexities of making certain choices. This was the problem of adding 2 linked list-based integers. Fairly straightforward, but it still demonstrated some core concepts about linked lists.